Hello, my name is Cindy Atman and I'm the Director of the Center for Engineering Learning and Teaching, or CELT as we call it. In this presentation, I'll briefly describe our center and our operational model, and then I'll provide a recent example of some work my colleagues and I have been doing to put that model into action. CELT was established in 1998 in the College of Engineering at the University of Washington. We're the first center in the nation in a College of Engineering to combine both a research and instructional development mission. Our mission is to conduct internationally recognized research in engineering learning, to promote teaching effectiveness in engineering classrooms at the University of Washington, and to be a model for effecting change in colleges of engineering. The first two, research and instructional development, are the foundations of our model, and we believe that the better we are at meeting those missions, the better potential this model will have for effecting change more broadly. Over the past decade, we've been conducting in-depth research on engineering design processes. We also study how engineering students integrate knowledge gained through classes and other learning experiences, and how this relates to the development of a professional identity. Additionally, we examine the instructional challenges of engineering educators and the effectiveness of instructional and curricular innovation. Our instructional development services include one-on-one consultations, as well as needs-specific workshops and seminars in which we help engineering faculty base their teaching practices on well-grounded understanding of research on teaching and learning. We also provide expertise on systems-level improvement initiatives. This slide shows how we see those research and instructional development activities integrated within our operational model. We draw findings from research that we conduct at CELT, engineering education research in general, as well as findings from learning sciences research more broadly, and we develop ways to communicate that research to our faculty and to ground our instructional improvement efforts in the most recent and relevant research. I'll now give an example of this model in operation. Recently, we worked with two engineering colleagues on seminar projects in which we brought findings from some of our design learning research directly to students in their courses. The study we referenced in these projects was published last year in the Journal of Engineering Education and won the William Elgin Wickenden Award for Best Paper published in the Journal of Engineering Education in 2007. The overall question we investigated in this particular study was, how do years of experience shape individuals' engineering design processes? This study involved both freshman and senior engineering students, as well as practicing engineering experts. In a lab setting, we asked our individual participants to design a community playground. They were given basic design parameters and were told that they could ask for any information they needed from the researcher. They were given 3 hours to complete the design, and they were asked to think aloud during the process. We audio recorded their design sessions, and those transcripts were then segmented and coded using a rigorous intercoder process. We analyzed the data in several ways, including determining the quality of the final design, identifying the kinds and amounts of information requested, and developing representations of their design processes. Their design processes were coded using a generic list of design activities that were previously synthesized from 7 engineering design texts. To better understand the interactions and transitions among the design activities, we find it useful to visually represent the coded data in a design process timeline. Shown here is an example of such a timeline. Time is represented on the x-axis and increases from left to right. The 8 design activity codes are listed on the left. For each activity, a separate timeline indicates when and for how long the participant was engaged in that activity. Here we see that the participant initially engaged in problem definition, gathered a little information, came up with an idea or two, did a great deal of modeling, and briefly resumed defining the problem near the end of the design process. Overall, we find the timelines to be powerful representations of design processes. They provide a direct means for understanding both the time allocation and transitions among design activities in someone's design process. In addition, by placing multiple timelines together, we gain insight visually into the differences in the design processes across individuals. A quick glance at these 3 timelines suggests several differences. This particular freshman moved into modeling quickly, while the seniors spent a little more time scoping the problem before going into modeling. The experts spent even more time in problem scoping and tended to frequently transition among all the design activities. Here are some findings from that study. Overall, the primary differences between the experts and the students were in the areas of problem scoping and information gathering. This suggests important competencies that engineering students need to develop. When these findings were shown to engineering faculty, they agreed that these were major problem areas in students' design work. Findings from this research form the basis for the interactive seminars we created in collaboration with 2 engineering colleagues. The first seminar was presented in a capstone course with 38 senior-level students. The second seminar was presented to 35 junior-level students working on a team-based design project. Our plan for both seminars was simply to introduce the research, let the students tell us what they interpreted from the timelines, and then collaboratively compare their insights with our research findings. Shown here is what the students were given to work with. The timelines illustrate typical freshman and senior timelines with low, middle, and high quality scores. The students were quickly engaged by the timelines and readily understood the representation. Their analyses resulted in several important insights and very active discussions in the student teams. Here are a few of those student insights. These are typical of the types of things students took away from these very simple exercises, and rather than us telling them what we think is important to know, they built that understanding themselves. These were exactly the kinds of concepts the professors wanted their students to think about and apply in their own design processes. We found this one particularly intriguing. The notion that an effective design process may be characterized as having a particular shape is something our researchers previously recognized and called a cascade pattern. That pattern, or what the student is calling an ideal project envelope, is most often seen in the expert timelines, contains a full range of design activities, suggesting a way of moving through those activities over time. After we had discussed their insights, we showed the students some of our research findings and discussed with them some comparisons we saw between student and expert data. We ended each seminar with a request for feedback. Here are a few of the things they said were important takeaways. It was gratifying to see how quickly students grasped important concepts from these seminars. These interactive seminars not only benefited students, but by working collaboratively with engineering faculty in the planning and implementation of these seminars, we were able to concretely demonstrate important pedagogical principles, such as the need to provide students with opportunities to construct knowledge actively rather than trying to absorb it passively. Additionally, by asking students and instructors to bench test our findings, we got a better idea of their usefulness and clarity, and we also learned what students view as important, information we will feed into our future research efforts. We're now planning for the coming year. The CELT team is refining the seminars and developing instruments that students can use to monitor, record, and plan their own design processes. We also hope to publish all of our design timelines so that other engineering educators might use them in their teaching. Please feel free to contact us with questions or for a complete list of our published research.